Okay, let's take a good example in terms of matrices. So suppose we have so let's write the Hamiltonian as such way that we have some Q and some P. And then we have some so it's like a Taylor expansion kind of thing that we can write the Hamiltonian as a quadratic form. So it also of course has like a 0 point, like a constant value and first order value, but we have chosen to expand it in the minimum. So that's sort of, and then we can get 1/2 on the second order expansion from the Taylor series. And these are first order, but there's 2 of them, so that's also fine. And then we can so then we can define the gradient of this one. So we have like nabla h, and that will be just given as this part. So and then for the sort of Poisson bracket, we can just, so you can see that this there's a switch. So we have gradient of something with respect to P and Q of that one, and then we have like a minus sign, and we're switching between Q and P. So now if we are defining some general vector Z, we can define a matrix J, which then switches these two. So we have something 0, n times n, identity, n times n, and then we have the minus sign from the Poisson bracket, and so now the Hamiltonian equations in matrix form may be written as so Hamiltonian equations as such, those were dot z equals to the Poisson bracket Hamiltonian with respect to z. So that was the Hamiltonian equation, and in matrix form we may write it now as dot z. Now z is a row vector, equals to the j times nabla of h with respect to z. Like so. And if we have this, so let's call this matrix here like I would like to call this matrix H as well, so let's call it like lowercase h. So we can also say this, it's J times H Z. So there's the 1/2 term, so we take the partial derivative. So there's q and q, so that's q squared, and then 1/2 cancels, and so on. So that's that. And so now suppose that we look at our propagator we just derived. So our propagator, we had J times H1 and H2 and so on. So the split propagator, it looks something like this now. That we have z at t plus dt, and it will equal to the old one, then plus, then derivative of the Hamiltonian with respect to p, for example, times the q. Well, I need to write it more explicitly, so I will just write this completely open now. So we had only the time derivative here, and I will write the p and q also. So p, q, and p. So, and we had time derivative of these ones, and then they equal to j. So j is now given as 0, 1, minus 1, 0. And then we have the Hamiltonian, and then we have this one. So let's see if it does it now look correct. Like so. Yes. And then to be even more explicit, we can, so that we can say that it was this sort of transformation that in some next time step. So firstly, of course, we want to have like identity. So it's the old one, then plus this one times dt. So back in P matrix. So let's take this as a common factor. So it's actually that we have some sort of identity matrix 0, 1, 0, like so, and then plus this matrix which had the dt, and then all of these will be multiplied with the p and q. So let's see how it looks like now. Okay. And so, and I will call this some other t prime time, because we are not actually, all of these propagators are sort of in the next step. Okay. And now it's actually worthwhile to see what the full propagator looks like. So we have this thing. So there's 3 steps to this. So first one, second one, and third one. And the first one was that one, and the second one was that one, but then the middle one was about the potential energy. So it was 1/2 omega squared m, and here was 0, like so. And so and then there wasn't, so it's then we can, for example, look, we could explicitly calculate this one, but let's not do it right now, but let's just calculate it explicitly here. So we have defined identity, so we have identity times j times h1 times dt divided by square root times I, then plus j times h2 times dt times I times plus j times h1 times dt. Okay, so we have this matrix here, and then we have this matrix. So it has 2 eigenvalues, and these eigenvalues are 1. And the thing is that these eigenvalues are also, so what if I have my 1 divided by those eigenvalues, they're also the same. So these are in unit circle, these eigenvalues, and the complex conjugation on the unit circle is equals to the inverse. So this matrix is symplectic matrix, and what it means is that j minus j times g times j should be 0. No? How was it? G times g. No? Let's just call symplectic matrix. Okay, symplectic matrix should satisfy this. It was transpose, so G transpose J times G minus J is 0. Okay, so this matrix is symplectic. So it preserves the symplectic structure, and so this matrix is, we can call this now G. So it was G tau J. G plus J. Okay. So I think this concludes basics of the classical mechanics for now.